Welcome, everybody, to the third lecture in Noam Chomsky's lecture series for this UCLA linguistics mini course. There will be a question period after the talk, and without further ado, I give you Noam Chomsky.
Yesterday I talked about some of the things that work out, some of the successes in finding genuine explanations, a term that I had discussed. That's actually something really new in the history of the subject. Till recently, even the concept of genuine explanation wasn't well understood, and there were no examples of it. But one of the striking things of the past few years is that there are some genuine explanations in the sense that I discussed for some quite fundamental properties of human language, and there are some rather surprising consequences which overturn long-held beliefs. Well, that was the successes. Today I want to talk about some of the failures, some of the things that don't work, and what they imply, and some of the ways around them. And we'll see that those too have some curious and unexpected and rather interesting consequences. So let's start with, start with X-bar theory. X-bar theory had some successes, some failures. One of the successes was that it eliminated the major problems of phrase structure grammar, the fact that phrase structure grammar permitted vastly many rules that are totally unacceptable, that couldn't be tolerated. Also, phrase structure grammar conflated three distinct properties of language: compositionality, linear order, and identification of the categories, projection. And X-bar theory separated linear order from the other two, which has lots of consequences that I discussed last time. There were problems. The problems were two. One, it still conflated two distinct concepts, joining things together and identifying their category. And secondly, and even more fundamentally, it ruled out exocentric constructions, which abound in language. They're all over the place. And that required all sorts of artifices to try to figure out how to get what you knew was more or less the reasonable answer, but without any justification for it. So we want to get rid of that. And the simplest way to get rid of that, the most principled way, is to assume the strong minimalist thesis and see how far you can go from there. That means you take the simplest compositional operation, the one that has to be embedded in any computational procedure, and see how much can be explained in those terms. And I discussed some of the successes last time. However, there's an immediate problem. What about exocentric constructions? So suppose you're constructing a subject-predicate construction. They have to be done in parallel. You have to construct the verb phrase and the noun phrase before you can merge the two together. That means you have to have a workspace in which things are constructed. And the workspace will consist of, first of all, the atoms of computation, call them lexical items, and anything constructed by the rules. So the workspace is just the set, including the atoms and anything constructed by merge. So that means oh, okay, thanks. not used to this high technology. So when you're, let's call this capital merge because it's different from the concept merge that has been used in recent years. So merge actually is going to take two things and put them together, call them P and Q, and the workspace. It's an operation on the workspace which is going to change it. Okay, so it's a much broader operation. And that's going to yield, as a notation, the workspace is a set, okay? It's a set which includes everything that's been constructed. But it's a different set, different kind of set from the sets that are formed by merge. It's not accessible to computation, so you don't merge the workspace with things. So just to indicate that, I'll use a different notation. I'll use square brackets for the set that is in fact the workspace. So the result of this will be merging P and Q, and then a bunch of other stuff. And that will be the resulting workspace. And that raises the question, what's here? Okay, so what's the rest of the stuff? Well, let's take the simplest case, the case where the workspace, where these are the only elements of the workspace. Okay, so the simplest case is a workspace that consists of P and Q, and then we ask, what does that yield? So it yields the set PQ, and what else? Well, if this was normal recursion, the kind of recursion that goes generally, applies generally, the rest of the workspace would include P and Q. Okay? So for example, if you're doing, say, proof theory, general recursion, you have axioms, you have rules of inference. If you apply the rules to either the axioms or some theorem you've already constructed, you get a new theorem, and what's left to what is accessible to further operations is everything that's already been produced, the axioms and every previous theorem. So that is essentially saying you include the set PQ you've just formed and P and Q. However, that fails for human language, and it fails in a very straightforward way. For example, if you were to do this, then you could take this guy here that you formed, you could turn it into something of arbitrary complexity, violating every imaginable island or any other property, and then you could merge this to it. You would get set PX, but this guy would be a copy of that. You would now have violated every linguistic property. All islands would be violated, no matter how radical they are. So that tells us that there's something different about recursion in human language and general recursion. We have to bar the things that were already there. They can't remain in the workspace. That raises interesting questions. Actually, I should say that the original definition of merge back in 1995 actually incorporated this property, but without recognizing it. It was really, if you look back at it, it was an operation that said replace. Said replace P and Q by the set PQ. And the formalizations of this, if you look at them, did add an operation remove. So get rid of things that you've already had. That we don't want. We don't want to have extra new operations. It should be that the right concept of capital merge just has this property. But that raises the question, why do we have that property? Why should language have the property that it deviates from normal recursion by getting rid of the things that had been generated, and you're not allowed to access them anymore. Well, that raises an interesting question. We would, of course, like to reduce this to some general principle, some essentially third factor property. Remember that in the study of growth and development, acquisition of language in particular, there are three factors you have to look at. One is what's genetically determined, that's UG. The second is whatever the data happen to be. And the third is independent principles that hold independently of the operation in question. That would include laws of nature and special things about the system that is carrying out the operation. So some properties of the brain in our case, which make it language ready. That's been noted for a long time, but nothing was ever said about properties of the brain, about which very little is known, in fact. But what we would look for in this case is some property of the brain that forces this. That would be a third factor principle. That would be the optimal conclusion. Before coming to that, let me notice that there are already embedded in linguistic theory as it's developed over the past years some examples of this. One case is that merge, in the old sense, never increases the workspace. The only way to increase the merge itself doesn't increase the workspace unless it happens to be bringing in a new lexical item. Okay, so the old definition just didn't allow arbitrary expansion of the workspace. More interestingly, conditions like the phase impenetrability condition, I apologize in advance to the number of faces in the audience. I'm going to assume familiarity with recent linguistic work with no time to go into the details. But the phase impenetrability condition, which is a fundamental condition with many important consequences, actually has the property of reducing accessibility to computation. It says there are things you've produced you can't see anymore, okay? That restricts the resources available for computation. Another case is simply C command. If you think about successive movement of something, we take it for granted that if you're doing successive cyclic A bar movement, let's say, the next move will pick the top element, not the lower elements, okay? Well, what that means is you're using essentially minimal search. You're using a computational principle, third factor principle, that says, look for the shortest thing and don't go any further. Well, again, that reduces accessibility. But we need something beyond. We already have a number of things have already been proposed that reduce accessibility and hence limit the richness of computation, but we want something beyond that. And actually there is something highly suggestive, a property of neural computation, which has been noticed elsewhere. The main, a very striking principle of computation is that the neural computation is that the brain is very slow. It's a very slow computer. And that shows up in pretty dramatic ways. I'll quote from Sandue Fang, a cognitive neuroscientist who's a colleague at Arizona, quoting him. The marvel that we call the human brain is actually the weak link in our cognitive apparatus. Our sensory apparatus far outstrips the brain's capacity to process the high resolution input to the sensory organs. The eye responds at a single photon level, the minimal possible detection. The eardrum vibrations respond at a level smaller than the diameter of a hydrogen atom. So not for everybody, incidentally. I'm an exception, but in principle, in principle it does. If you think about that, it's pretty remarkable. And it's the same for every sensory system. They're essentially perfect, physically perfect. The brain can't handle that. So almost all of the computation that the brain is doing is throwing out information. The brain is incapable of handling the amazing capacity of the sensory system to be optimal, physically optimal detectors, better than anything that can be constructed. It does raise a strange question. Why did Mother Nature bother to produce these astonishing systems if the next step is to get the brain to throw out all the information that they produce? That's not just true for humans, it's true for all organisms. It's a question. You could ask why that happened. Probably there's some basis in physical law that explains, unknown principle of physical law that explains that if you're going to have sensory systems, you have to make them perfect. But what the reason for that is unknown. It just is a fact. Anyway, the brain is essentially throwing out almost everything that comes in, and it's very tempting to think that the resource limitation that's part of language computation, and presumably part of the computation that's done by any organism, that it's just a special case of the fact that the brain is so slow and incompetent. It wants to get rid of tons of information. That's a plausible candidate for the conclusion that one of the properties of linguistic recursion, as distinct from recursion in general, is simply that it's got to work through the brain, which remember that whatever the properties of the brain are that implement the linguistic computation is some third factor condition which is just presupposed by language, presumably by any organic computation. Well, if you think back a step, we've been trying all along in the concept of general, genuine explanation to restrict the amount of computation that takes place, to find the simplest theory, the one with the fewest mechanisms, least computation. And there were good reasons for that, which I discussed. One, just the general fact that simplicity of theory corresponds to depth of explanation, which is what you're trying to achieve in any serious scientific inquiry. Secondly, there's this Galilean precept, which has been spectacularly successful about nature being simple. And third, in the special case of language, there are the empirical conditions on language evolution, which we don't know for certain, but seem to show, as I discussed, that it was a very sudden, immediate development, which hasn't changed since, and of course very recent in evolutionary time, all of which converge to suggest that computation should be restricted to the minimum. Here we have a second point. Not only should computation be reduced to a minimum, but the resources available to computation, the set of elements accessible to the operations, that too should be reduced to a minimum. And so we seem to have a very broad principle of reduction of computation, broader than normal explanation in the sciences, which says not just are the means restricted to the minimum, but also the resources accessible to the means have to be restricted to the minimum. Now, that has a lot of consequences. One consequence is already mentioned, tells us that the workspace is going to be as small as possible. Well, Let me just make a comment on notation. We want to say that this, the workspace, which is a set containing X, is distinct from X. Okay. We don't want to identify a singleton set with its member. If we did, the workspace itself would be accessible to merge. However, in the case of the things produced by merge, we want to say the opposite. We want to identify singleton sets with their members. This is actually something that goes back to phrase structure grammar. In phrase structure grammar, you didn't allow rules that would look like this. V arrow V, let's say. That nobody said why, but it's just the kind of thing it didn't do. It's not allowed. For one thing, it would get you into infinite loops. You don't want that. So it was just kind of barred. Now, there was a trick used in phrase structure grammar, an illegitimate trick, which introduced VP. So if you had a verb that was a verb phrase that was only a V, it would be described like this. I'm using the free notation just because it's easier to describe. So you could have, say, NP, VP, this guy could become V. Okay. That's barred by X-bar theory. Okay. In X-bar theory, you don't have any VP if it's only a V. That was taken for granted in X-bar theory. Actually, it has consequences. For one thing, for Richie Kane's linear correspondence axiom, LCA, it was necessary to introduce VP if you want to get the asymmetry between a subject and a verb. But that's illegitimate. So it's a problem for LCA, and there are other consequences. Carrying that over into the merge framework, what it comes down to is this. Okay. So crucially, in the case of the workspace, we do not identify a singleton set with its member. In the case of something constructed by merge, yes, we do identify a singleton set with its member that has quite a number of consequences. Well, this actually, simplest case that I just mentioned actually provides a criterion for determining what are the proper and improper forms of merge. We have to ask for every notion of merge that's developed, every case that's proposed, whether it yields illegitimate derivations. If it does, we have to throw it out. So take something that I think nobody's ever proposed, but let's just imagine it. I suppose we have, call it A and B. We've constructed a syntactic object that looks like that, and then we want to merge A and B. Okay, so that's going to give us, let's call this guy X. It's going to give us the result, the set A, B, and X. Okay, so suppose there's nothing in the original definition of merge that blocks that. It's just something nobody ever wanted to do because it doesn't make any sense. But suppose you do it, then what happens? Well, same story as this. X can become arbitrarily complex. Let's call it Y. A can adjoin to Y. A is in here, remember. And we've again violated all conditions. Okay, so this is ruled out because it allowed too much accessibility. We want a definition of merge that restricts accessibility so you won't be able to get things like that. Well, that was something that's never been proposed. But let's take things that have been proposed and are very widely used in linguistic description, like, for example, what's called parallel merge. Okay, parallel merge is usually described like this. What you do is construct a tree notation in which the element B is part of BC and also part of AB. That's called parallel merge. Well, I should make a comment at this point. The tree notations are kind of convenient, but they're very misleading, and you should really pay no attention to them. For one thing, a tree notation kind of leads you to suggest that there's got to be something at the root of the tree, but that's conflating compositionality with projection. And in fact, you just often don't have things at the root of the tree. For example, every exocentric construction. Okay, that's what labeling theory takes care of, which eliminates that conflation. Another reason is that when you draw trees, it looks easy to do lots of things that don't make any sense. So especially with contemporary computer graphics, you can draw funny lines from one point to another and connect those two things. Or you can tack something in lower in the tree and call it late merge and so on. And it seems to sort of work out by playing around with trees, but if you try to translate it into merge, it doesn't make any sense. So let's take parallel merge. What this really means is that you started with a set AB, and this is the workspace now, and it had C in it. And then what you did was merge B with C, which gives you a new workspace, WS prime, which consists of the original set and a new one. Okay. And here we have the old problem. The problem is we can turn this into something as wild as we want, and then we can merge this to it, and we have a connection between these two, which violates every possible condition. So parallel merge looks as if it's easy to draw, but can't be a legitimate operation because, again, it violates this paradigmatic problem, which tells you that you're proposing an operation which is going to yield illegitimate objects that violate every imaginable syntactic condition. So that has to be ruled out. Actually, those of you who know the literature know that parallel merge has been used to give lots of interesting results. It's the basis for trying to construct what's called multi-dominance, constructions where you have a mother connected to different things down below. That's been used for cross-the-board deletion, for lots of other things, to give accounts of these things. Now, those in the literature are called explanations, but they're not. They're descriptions. They're interesting descriptions, which have the property that I discussed earlier. They're illegitimate ways to impose some kind of organization on chaotic data, which is very useful often. It says, well, now it's more organized than before, so we can kind of look and see if there's a possible way of accounting for it. But it's not an explanation. It's a way station on the way to conceivable explanation. So there's got to be something about the definition of merge that's telling you you can't create parallel merge. And if you think about it for a second, you can see what it is. There are too many accessible things being produced. Okay. The right definition of merge, when we get to it, should allow only one new accessible object, namely the one you're constructing. When you put P and Q together, you're constructing a new object, the set PQ. That's accessible to computation, but nothing else should be. That should be the right definition of merge. This one is adding two new accessible objects. It's adding this one, but also this one. Okay, and that's too many. The right definition of the computation should permit only the minimal number, namely one new accessible object. And again, I suspect that that goes back to the general property of the brain that says it's just very slow. It has to throw out information. Actually, before going on, I might mention that this is kind of familiar in other domains of language acquisition. So when you study the acquisition of phonology in infants, what you find is, of course, every infant is capable of all the phonemic distinctions in any possible language. But by about a year old, or maybe even earlier, most of them have just been lost. What the early stage of phonological development is doing is saying, throw out all the possibilities and just leave us with these. When you study critical periods in language acquisition, it's pretty much the same. What you're saying is that these apparently several critical periods, lots of stuff is just thrown out that you're not allowed to look at anymore. That's what makes a critical period. If you look at a general, take a theory of language acquisition like, say, Charles Yang's, which assumes that the child just starts with all the possible I languages, and as data comes along, the probability distribution over the set of I languages changes. Okay, so some data comes along and says, okay, I'll lower the probability of this guy and raise the probability of that one. And ultimately, in the course of language acquisition, it need not converge in a single point, but it gives you a skewed probability distribution in which many things are kind of way down there. You're not going to bother with them. And there's a few or maybe a couple of things that are high probability, so you hang on to those, and that's your I language. You could again describe that in the same terms. It's saying what the acquisition system is doing is simply throwing out lots and lots of data. What we know the brain does massively because of the extraordinary sensitivity of the sensory organs. Well, anyhow, a parallel merge goes, and with it, all of the interesting, very interesting empirical consequences that have been produced that are based on parallel merge. Now, those consequences remain, but as puzzles, not as things that have been explained, as kind of organized data, which now we want to look at. Take a look at, say, what's called sideways merge. Same problem. I won't run through it, but if you formulate sidewards merge, not just as a tree, with a line going from here to here, but in terms of actual merge, has exactly the same problem. So this problem here, the very simple problem, this one, turns out to be a very good diagnostic to tell you when some proposed concept of merge is legitimate or not. It's very simple idea, and it cuts very deeply. Let's take late merge. Well, late merge has the same problem, but an additional problem, which was pointed out by EKS, Epstein, Kitahara, Seeley, namely late merge. In the case of late merge, where you're sort of tacking something on down here somewhere, one, it has the problem I already mentioned, but secondly, it requires a substitution operation. Namely, this guy has to go back here. How does that happen? Well, you know, when you draw a tree, you just draw it there, but that's not enough. You need some kind of operation that says the new thing you've constructed has to go right in the position of what you've constructed it from. It's a non-trivial operation, but it's way beyond the bounds of SMT. So late merge, which has lots of consequences, it's used very widely, also can't be correct. And in fact, I think most of the late merge literature, I won't have time to talk about this, probably reduces to ellipsis. But I'll put that aside here, just a problem to work on. Anyway, all of these things are out. All the consequences that follow from them, there's lots of stuff in the literature, very interesting consequences. They remain as just puzzles. Well, if you think about these proposals, they do fall within the original loose and vague characterization of merge. So it's natural that people should have proposed them. They seem to fall within the original, I won't say definition, because it wasn't clear enough to be a definition, but the original characterization of the idea. And it's led to interesting results, but misleading interpretations of them. They are not results. They're simply presentations of interesting data, which we now have a problem about trying to figure out what. Well, that suggests a research program. The research program is, first of all, to take all of the kinds of operations that have been proposed for merge, ask yourself which ones are legitimate and which ones are not legitimate. And then the second task is to formulate a new definition which captures just the legitimate ones, leaves out the illegitimate ones. And then the third part of the research program is to explain why. Okay, so those are the three steps. I'll skip the first step. There's a lot of material in the literature showing which ones are legitimate, which ones aren't. It runs right along essentially the lines I've just outlined. It turns out that the only ones that are legitimate are the simple ones that we had in mind when it was first developed. Narrow external and internal merge. All of the rest, parallel merge, sideways merge, late merge, other proposals have been made, they're all illegitimate. Illegitimate on the very same grounds. They yield legitimate operations which produce illegitimate results, hence have to be excluded. And they all have the property that they're increasing accessibility too much. So that's the first part. We then want to formulate merge so that it'll block these things. We'll want a definition that looks like this. Actually, that'll do it. Where we have to say something about this. Okay, what do we have to say about it? I'm going to skip the formalities. It's easy to formalize all this, but too much trouble. You can do it yourselves. Just intuitively, what it does is say that the first condition that has to be met by this new definition is that nothing that was in the workspace can be lost. Okay, you can't throw out stuff from the workspace. So if something was there and is distinct from P and Q, of course those we're operating on, but anything else that was there still has to be in the workspace. Okay, so that's the first condition. Second condition is that the new definition of merge has to be minimal, the optimal definition. It has to restrict accessibility as fully as possible. Now, merge itself is creating one new accessible object. That's the point of merging. You're creating a new object, but it can't allow anything else to be accessible. Okay. That's the second thing. And the third is just we don't want any arbitrary junk around. So not a lot of other stuff that had nothing to do with the operation. Those are basically the conditions on the proper definition of merge that leaves us for the next step. What's the explanation for it? And here we have now we basically have the explanation. The first point that says you can't throw things out is actually a special case of the no tampering condition, the general SMT condition of minimal computation, which says you can't modify the elements that are entering into the computation. Well, the most extreme form of modifying something is to throw it out, okay? So you can't do that. So that's the first condition. The second condition is the resource constraint. The resource constraint, which I think probably reduces to a general third factor property of the nature of the brain, the slow element in the cognitive system, the thing that's hampering cognition, the brain. So it probably just goes back to that. So we have the resource constraint, which limits accessibility. The third thing that says don't throw in any extra junk is actually a consequence of the restricting accessibility. If you throw in anything else, you're increasing accessibility. Okay, so we therefore have an optimal definition of merge, capital merge, which meets all the conditions we want, and we have an explanation for all of them. So that's the set of flaws, failures, and a possible solution for all of them, a plausible one. Well, there's something else that we have to point out here. I'm skipping a lot of things, so it doesn't matter. There's another consideration that we have to keep in mind. Let's call it stability. The general property of computations, which we don't usually bother to think about, but we have to be explicit about it for reasons that show up when we try to explain things. So, for example, if you're forming, say, a topicalization, you say Mary's book I want to read. And remember, down here we have Mary's book, because it's the optimal internal merge operation, which doesn't delete anything. When we pronounce it, we drop the lower copy, but that's again for reasons of computational efficiency. But we're now talking about just what reaches the mind. We're forgetting about what reaches the ear, the extraneous stuff, which doesn't really belong to language, strictly speaking. Something that's taken for granted about this, but that we have to be clear about, is that the two occurrences of Mary's book have to be absolutely identical in every respect. So it can't be one Mary up above who's the topic and another Mary whose book we're reading. It can't be that the topic is the book that Mary owns and the copy, the thematic object, is the book that Mary wrote, let's say. That's simply taken for granted. The interpretive system has to know when things are precisely, absolutely identical. So let's call that condition stability. Turns out to be consequences. Now that immediately begins to raise some interesting questions. What's a copy and what's not a copy, a repetition? So you can pick things out of the lexicon, which are totally different but happen to be identical in syntactic and phonetic form. So you can say, John saw John. Okay, that's okay, but those are two different Johns. They have nothing to do with one another. Those are repetitions. On the other hand, here, when you've done internal merge, you have copies. How does the interpretive system know what's a copy and what's a repetition? Okay, they look alike, but it has to know them. Now, that turns out to be a non-trivial question. There's an interesting paper by Eric Grote and Chris Collins. It's on, I don't think it's been published, but you can find it on LingBuzz, where they just go through a lot of the problems in the various efforts to explain this. But you have to be able to explain it. The interpretive system's got to know what's a copy and what's a repetition. Now, I'm assuming here phase theory for good reasons. That means that at the phase level, precisely at the phase level, the system has to know the distinction, okay? Well, of course, at the phase level, you do have the information about what was produced by internal merge and what was produced by external merge. So you can see, you have some information, but it's not complete, because there are cases of internal merge internal to the phase. Like, for example, raising the subject to subject position inside the CP. It's internal to the phase, but it's, and at the phase level, you don't see that it's just happened here. So how can the interpretive system solve this problem? That raises quite interesting questions. And I think the basic answer to it is given by a general property of language, which is sometimes called duality of semantics. If you look quite generally at interpretation of expressions, it falls into two categories. There's one category which yields argument structure, theta roles, and the interpretation of complements of functional elements, okay? Basically argument structure. There's another category which is involved in displacement, which has kind of discourse-oriented or information-related properties, or scopal properties and so on, but not argument properties. Okay, that's duality of semantics. You think about it a little further, you see that the first type, argument structure, is invariably given by external merge. The second type, non-argument structure, other factors, is always given by internal merge. Now, there appear to be some exceptions to this. As usual, when you produce a generalization, you look at details, you find maybe something didn't work. If it's a strong generalization, the proper approach, just as standard science, is to say the exceptions are probably misunderstood and make the strong generalization work always. I think that's a good rule of thumb used constantly in the sciences. We should use it here. So I think duality of interpretation is probably a very strong principle. The question is, where does it come from? Well, probably it's just a property of the nature of thought. We don't know a lot about thought. In fact, one of the main ways in which we come to understand thought is to ask how it's linguistically articulated. That's one of the very rare avenues into what's the nature of thinking. And if it's correct, as I've been suggesting throughout, that language really doesn't care about use or communication. That's kind of irrelevant to language. It cares about expression of thought. Then we'd expect the design of language to capture these fundamental aspects of thinking, okay? That's what I'm proposing. Now, if you think about duality of semantics, you have a technique right away to determine what's a copy and what's a repetition. If something is in a theta position, it's a repetition. If it's a unless it's been raised, in which case it's a copy of what's been raised. If it's in a non-theta position, it's a copy. Okay, and at the phase level, the system simply has to take a look and say, what's a theta position, what's in a theta position, what isn't in a theta position. That tells us what's a copy and what's a repetition. That cuts through the mass of the objections and problems that Collins and Grote pointed out. Now if we restate that, what we'll be saying is that the operation merge produces copies, always. Both cases of merge, external and internal merge. That produces copies, nothing else does. Okay? So a copy is just whatever's created by merge. In the case of internal merge, it creates two copies. In the case of external merge, also creates two copies. The original thing and the thing that's in the set you formed, but the operation merge, which is in effect a replace operation, gets rid of the first copy in the case of external merge, so you never see it. Okay? So merge always produces two copies, but external merge, just by the nature of the operation, the minimal operation, yields only one of them remaining. Okay, that's the resource restriction part. Okay, now that still raises some interesting questions. If you start thinking of the complexity of constructions, double object constructions, topicalization, small clauses, and so on, it looks as if there are ambiguities in searching for what is a copy of what. And what we have to show is that language has a conspiracy that determines the answer in each case. So, for example, in the case of double objects, Vergniaud's abstract case theory, if you think about it, uniquely determines the answer. In the case of topicalization, when you want to know you have a topic up there, you want to find out which of many things that look identical it comes from. If you think about, say, Luigi Rizzi's left periphery theory, plus the theory of labeling, which determines criterial positions, it'll solve that problem. The case of small clauses is extremely interesting. Well, if there's time, there's not time today, but if there's time tomorrow, I'll come back to it. But there's an interesting way of resolving that ambiguity. But here's a problem that I pose. There has to be a conspiracy in the structure of language that automatically resolves ambiguities about what's a copy of what. Okay, so we have two problems about copies. One, what's a copy and what's a repetition? That's solved by defining copy as just anything produced by merge and nothing else, and by duality of semantics. Then the second question, what's a copy of what? That has to come from some internal conspiracy about the nature of language. I think there are answers, but it's not trivial. You should think, I leave it as something to think through. I should point out, in addition, you can think about this, so I won't go into it, that none of this works for the illegitimate operations. So if you do sidewards merge or parallel merge and so on, and none of this is going to work out. There you do have the problems of copy, repetition, and identification. That's an independent argument to show that the illegitimate cases are illegitimate. The main argument is they just yield illegitimate outputs. But it also turns out that the concept of copy, repetition, and unambiguously finding copies fails for the illegitimate cases. You can try it out and see how it works for yourself. Well, notice that you can now rephrase the whole process of constructing merge and its application. You can rephrase it in terms of the normal way in which recursive processes are described. I won't bother writing it out. I'll just read it to you. It's simple. So suppose you want to define the set of integers. How do you define the set of integers? Well, what you say is the set of integers is the smallest set, the least set, containing 1 and containing the successor of any integer. Okay, that's the set of integers. That's transitive closure, the Phrygian ancestral, the classic way. So what do we say here? Well, what we say is that for a given I language, the set of set of workspaces is the set, notice, not the least set. It's the set containing the lexicon and containing merge PQ workspace for any PQ and workspace that's already been generated. Okay, it's the same as the definition, the transitive closure of the set of integers with one exception. We don't have to say the least set, simpler here. We don't have to say it because resource restriction already forces it to be the least set, okay? So essentially we're in the right ballpark. We have standard definition of recursive inductive definition under transitive closure of the set of workspaces, and it's exactly where we want to be. Well, there's a lot of, I've kind of skipped a lot of steps here. You know, there's a lot of things that have to be filled in, but I think maybe this is enough of a picture so you can see how they can be filled in. Well, let me just, to finish, turn for today. I want to go to some new topics tomorrow, another set of topics, but let's just ask what we can say about the things that are left unexplained. Okay, so let's take, say, ATB, across the board deletion. So, what book did John read and Mary buy, let's say? Okay, another one, thank you. Simple case of ATB. This is nicely handled in terms of multidimensionality and parallel merge, but unfortunately that's illegitimate. So we have to ask, is there a legitimate way of doing it? Well, if you think about this, the simplest approach is to say it just derives by deletion from what did John buy, and remember there's a copy here. What book? And what book did Mary read, buy? So just a conjunction of these two. So why doesn't it come from what did John buy and what book did John buy and what book did Mary read? Which also has what book here. Well, there's a standard objection to this. The standard objection is nothing tells you it's the same book in both cases. So that looks like a problem. However, notice we already have a solution to that problem. Namely, let's take a look at what the copies are. This is a copy. This is a copy. this is a copy, and this is a copy, okay? We have a principle, quite independent of this, that tells us that when we have a series of copies, the first one remains, all the others delete, okay? So we automatically get the right form, but what about the right interpretation? How about the fact that the two books might be different? Well, here the notion stability enters. Deletion, in general, has the property, quite generally, deletion in general, quite apart from this, as in the topicalization case and anything, ellipsis, anything else, has the property that you have to have absolute identity. Otherwise, you can't delete, okay? So if you want to delete under, say, VP ellipsis or topicalization or whatever it may be, there has to be absolute identity. That's the stability property. So in fact, it automatically turns out, without any comment at all, that you get ATB. Just follow the principles already established. Now there's something crucially important here. Namely, you don't have C command between these two. No C command. Suppose you did have C command, then it wouldn't work. So if you have the sentence, let's get an example that works. So which, I won't write it, it's too much trouble, but take the sentence, which book did John ask, which book did John ask sorry, I can't read my handwriting. Which boy did John ask which boy Bill met? Okay. Which boy did John ask which boy Bill met? Notice there you do have C command all the way through. That means that at the phase level, where you're getting the copy of which boy in the top case, it's in theta position, looking at a copy below it, which it C commands, that tells you it's a repetition by definition. So at the phase level, you know that these two things are repetitions, not copies, because there's a C command relation between them. So crucially, the lack of C command in coordination yields ATB, but the same effort will fail because of phase theoretic considerations when you try to do it in a case like which boy did John ask, which boy Bill met, and so on. You can kind of write it out and figure it out for yourself, but it all kind of turns out mechanically. There's nothing to say about it. Pretty much the same is true of parasitic gaps. You can try it on your own. So the standard examples that are used for multidominance and parallel merge fall into place without any comment. They just come from following the simple processes of minimal computation, resource restriction, and stability, the general principle of deletion. Well, the task is show this for everything, okay? Not a small task. I'll leave it there and turn to some other problems tomorrow. Okay.